Chapter 10 Extending the Limits of Tractability. Although we started the book by studying a number of techniques for solving problems efficiently, we've been looking for a while at classes of problems, NP-complete and P-space complete problems, for which no efficient solution is believed to exist. And because of the insights we've gained this way, we've implicitly arrived at a two-pronged approach to dealing with the new computational problems we encounter. We tried for a while to develop an efficient algorithm, and if this fails, we then try to prove it NP-complete or even P-space complete. Assuming one of the two approaches works out, you end up either with a solution to the problem and algorithm or a potent reason for its difficulty. It is as hard as many of the famous problems in computer science. Unfortunately, this strategy will only get you so far. If there is a problem that people really want your help in solving, they won't be particularly satisfied with the resolution that it's hard and then that they should give up on it. They'll still want a solution that's as good as possible, even if it's not the exact or optimal answer. For example, in the independent set problem, even if we can't find the largest independent set in a graph, it's still natural to want to compute for as much time as we have available and output as large an independent set as we can find. The next few topics in the book will be focused on different aspects of this notion. In chapters 11 and 12, we'll look at algorithms that provide approximate answers with guaranteed error bounds in polynomial time. We'll also consider local search heuristics that are often very effective in practice, even when we are not able to establish any provable guarantees about their behavior. But to start, we explore some situations in which one can exactly solve instances of NP-complete problems with reasonable efficiency. How do these situations arise? The point is to recall the basic message of NP-completeness. The worst-case instances of these problems are very difficult and not likely to be solvable in polynomial time. On a particular instance, however, it's possible that we are not really in the worst case. Maybe, in fact, the instance we are looking at has some special structure that makes our task easier. Thus, the crux of this chapter is to look at situations in which it is possible to quantify some precise senses in which an instance may be easier than the worst case and to take advantage of these situations when they occur. We will look at this principle in several concrete settings. First, we'll consider the vertex cover problem, in which there are two natural size parameters for a problem instance, the size of the graph and the size of the vertex cover being sought. The NP-completeness of vertex cover suggests that we will have to be exponential in at least one of these parameters, but judiciously choosing which one can have an enormous effect on the running time. Next, we will explore the idea that many NP-complete graph problems become polynomial time solvable if we require the input to be a tree. This is a concrete illustration of the way in which an input with a special structure can help us avoid many of the difficulties that can make the worst case intractable. Armed with this insight, one can generalize the notion of a tree to a more general class of graphs, those with small tree widths, and show that many NP-complete problems are tractable on this more general class as well. Having said this, we should stress that our basic point remains the same as it has always been. Exponential algorithms scale very badly. The current chapter represents ways of staving off this problem that can be effective in various settings, but there is clearly no way around it in the fully general case. This will motivate our focus on approximation algorithms and local search in subsequent chapters. 10.1 Finding small vertex covers. Let us briefly recall the vertex cover problem, which we saw in chapter 8 when we covered NP-completeness. Given a graph G equals to VE and an integer k, we would like to find a vertex cover of size at most k. That is a set of nodes S, which is a subset equals to V. of the size of S less than or equals to K, such that every edge E in E, little e in capital E, has at least one end in S. Like many NP-complete decision problems, vertex cover comes with two parameters, n, the number of nodes in the graph, and k, the allowable size of a vertex cover. This means that the range of possible running time bounds is much richer, since it involves the interplay between these two parameters. The problem. Let's consider this interaction between the parameters n and k more closely. First of all, we notice that if k is a fixed constant, e.g. k equals to 2 or k equals to 3, then we can solve vertex cover in polynomial time. We simply try all subsets of V of size k and see whether any of them constitute a vertex cover. There are n choose k subsets, and each takes time big O of kn to check whether it is a vertex cover for a total time of big O of k times n choose k, which is equals to big O of k times n to the k plus 1. So from this, we see that the intractability of vertex cover only sets in for real once k grows as a function of n. However, even for moderately small values of k, the running time of big O of k times n to the k plus 1 is quite impractical. For example, if n equals to 1000 and k equals to 10, then on a computer executing a million high-level instructions per second, it would take at least 10 to the 24 seconds to decide if G has a k-node vertex cover, which is several orders of magnitude larger than the age of the universe. And this is for a small value of k, where the problem was supposed to be more tractable. It's natural to start asking whether we can do something that is practically viable when k is a small constant. It turns out that a much better algorithm can be developed with a running time bound of big O of 2 to the k times kn. There are two things worth noticing about this. First, plugging in n equals to 1000 and k equals to 10, we see that our computer should be able to execute the algorithm in a few seconds. Second, we see that as k grows, the running time is still increasing very rapidly. It's simply that the exponential dependence on k has been moved out of the exponent on n and into a separate function. From a practical point of view, this is much more appealing. Designing the algorithm. As a first observation, we notice that if a graph has a small vertex cover, then it cannot have very many edges. Recall that the degree of a node is the number of edges that are incident to it. 10.1 If G equals to VE has n nodes, the maximum degree of any node is at most D, and there is a vertex cover of size at most k, then G has at most k times D edges. Proof. Let S be a vertex cover in G of size k prime, which is less than or equals to k. Every edge in G has at least one end in S, but each node in S can cover at most D edges. Thus, there can be at most k prime times D, which is less than or equals to k times D edges in G. Since the degree of any node in a graph can be at most n-1, we have the following simple consequence of 10.1. 10.2 If G equals to VE has n nodes and a vertex cover of size k, then G has at most k times n-1, which is less than or equals to k times n edges. So as a first step in our algorithm, we can check if a G contains more than k times n edges. If it does, then we know that the answer to the decision problem is there a vertex cover of size at most k is no. Having done this, we will assume that G contains at most kn edges. The idea behind the algorithm is conceptually very clean. We begin by considering any edge E equals to uv in G. In any k-node vertex cover S of G, one of U or V must belong to S. Suppose that U belongs to such a vertex cover S. then if we delete u and all its incident agencies, it must be possible to cover the remaining agencies by at most k-1 nodes. That is, defining G minus the set of singleton U to be the graph obtained by deleting U and all its incident agencies. There must be a vertex cover of size at most k-1 in G minus the set of singleton U. Similarly, if V belongs to S, this would imply there is a vertex cover of size at most k-1 in G minus the singleton set V. Here is a concrete way to formulate this idea. 10.3. Let E equals to UV be any edge of G. The graph G has a vertex cover of size at most k if and only if at least one of the graphs G minus the singleton U and G minus the singleton V has a vertex cover of size at most k-1. Proof. First, suppose G has a vertex cover S of size at most k. Then S contains at least one of U or V. Suppose that it contains U. The set S minus the singleton set U must cover all agencies that have neither and equal to U. Therefore, S minus the singleton U is a vertex cover of size at most k-1 for the graph G minus the singleton U. Conversely, suppose that one of G minus U and G minus the singleton V has a vertex cover of size at most k-1. Suppose in particular that G minus the singleton U has such a vertex cover T. Then the set T union the singleton U covers all agencies in G. So it is a vertex cover for G of size at most k. Statement 10.3 directly establishes the correctness of the following recursive algorithm for deciding whether G has a k-node vertex cover. To search for a k-node vertex cover in G, if G contains no agencies, then the empty set is a vertex cover. If G contains greater than k times the size of V agencies, then it has no k-node vertex cover. Else let E equals to UV be an edge of G. Recursively checks if either of G minus the singleton U or G minus the singleton V has a vertex cover of size k-1. If neither of them does, then G has no k-node vertex cover. Else, one of them, say G minus the singleton U, has a k-1 node vertex cover T. In this case, T union the singleton U is a k-node vertex cover of G. Then we finish the double if box. Analyzing the algorithm. Now we bound the running time of this algorithm. Intuitively, we are searching a tree of possibilities. We can picture the recursive execution of the algorithm as giving rise to a tree in which each node corresponds to a different recursive call. A node corresponding to a recursive call with parameter k has as student to nodes corresponding to recursive calls with a parameter k-1. Thus, the tree has a total of at most 2 to the k plus 1 nodes. In each recursive call, we spend big O of k times n time. Thus, we can prove the following. 10.4. The running time of the vertex cover algorithm on an n-node graph with a parameter k is big O of 2 to the k times n. We would also prove this by a recurrence as follows. If t of nk denotes the running time on an n-node graph with parameter k, then t of ... satisfies the following recurrence, where ... means to input parameters for the function t. Okay, so then t of ... satisfies the following recurrence for some absolute constant c. That is, t of n1 is less than or equals to c times n, and t of nk is less than or equals to 2 times t of nk-1 plus c times k times n. By induction on k, which is greater than or equals to 1, it is easy to prove that t of nk is less than or equals to c times 2 to the k times n. Indeed, if this is true for k minus 1, then t of nk is less than or equals to 2 times t of n minus 1 k minus 1 plus c times k plus times n, which is less than or equals to 2 times c times 2 to the k minus 1 times k minus 1, then times n, then plus c times k times n, which is equals to, if we merge the base 2 with different exponential number, that will become c times 2 to the k times n minus c times 2 to the k times n plus c times k plus n, which is definitely less than or equals to c times 2 to the k times n. So in summary, this algorithm is a powerful improvement on the simple brute force approach. However, no exponential algorithm can scale well for very long, and that includes this one. Suppose we want to know whether there is a vertex cover with at most 40 nodes rather than 10. Then on the same machine as before, our algorithm will take a significant number of years to terminate.